All right. Hello, everyone. Thank you for tuning into the Corundum development meeting today. I'll go ahead and get these slides going. All right. So let's see. There's basically three main parts of the slides today. The first part is the announcements. Second part is some basic project ideas, and the third part is the status updates. So more on the project ideas in a minute because that's new but could be interesting. Okay. So the announcements is the next Corundum developer meeting is going to be in 2 weeks on the 28th, and the next Switch development meeting will be on the 21st. A week from today. All right. So if you're interested in Switch development, join us next week, and I'm going to mention a couple things about the Switch status at the end of the presentation today. All right. Let's see. So the product ideas is something that I figure it might be a good idea to talk about for anybody that's interested in getting involved with the development of Corundum, but doesn't really know where to start because it's a pretty big, complicated project. So the idea is that these are some relatively simple, self-contained things that somebody might be able to pick up and work on. All right, so I'm just going to go through a couple of these ideas real quick. I'm going to try not to take too long here. I can certainly go into a lot more detail if anybody has any questions. Later on we can revisit this and go into more details if people are interested. So if you see any of these ideas and you're like, hey, I'd like to work on that, hop on Zulip and get a hold of me and we can talk about it. The other thing I'll mention is that these are things that in general I would like to see in Corundum at some point in the near future. So I may end up working on some of these myself, depending. So, but if someone is interested in working on one of these, I will, do what I can to facilitate that. Yeah. Anyway, so some of these ideas are, let's see. First of all, doing oversampled gigabit Ethernet via the 10G transceiver. So under certain conditions, it's not really feasible to reconfigure a 10G transceiver to operate at 1 gigabit per second. So the question is, if we leave it configured for 10G, can we bring up a 1 gigabit link through that transceiver using some sort of oversampling, basically? So I think it should be possible, but I think it's going to require a little bit of testing to see if that's actually going to work. And then plus, we have to implement a gigabit PCS as well, or 1000 base X PCS that'll work in this configuration. So not particularly complicated, but could be interesting if you want to learn a bit more about the serial transceivers and Ethernet and whatnot. Next is open source 40G Mac plus PCS. Had a few people ask about, hey, does Corundum support 40G? Well, you can use whatever Mac you want. And if you have a 40G Mac, you could certainly use it. Xilinx does have a 40G Mac that you can use, but it's rather expensive soft Mac license that you need for that thing. There are a few bits and pieces of code floating around online that I've discovered recently that seem like they would correspond to at least most of a 40 gig Mac plus PCS, but it would take some work to integrate those pieces, and there may be a few additional pieces that would have to be written. Not sure. 40G Mac is going to be a bit more complicated than the 25G Mac that exists already, but it's significantly less complicated than 100G Mac plus RSVEC that you get with the CMac. So somebody's interested in working on that, certainly try to facilitate and make that happen. The next point on here is basically wrapper modules that integrate the Mac with the PHY and transceiver modules in such a way that they can be reconfigured for running at different line rates. So this one's mainly involves the addition of a few muxes and whatnot to make all the right internal connections. So we already have the ability to reconfigure the transceivers themselves for different line rates and changing a few other settings. But it's a matter of, well, okay, if we could extend that to the max, then you can potentially, with ETH-tool, pick whatever line rate you want and be able to reconfigure the design at runtime. So I have two different wrappers right now, one with the 10 gig, 25 gig PHY and the GT cores, and the other one with the 100 gig CMAX plus the GT cores. So the idea here is to make kind of a kitchen sink type wrapper that just has support for all of the standard line rates. So I mean, I list all these different rates here, but it's more like whatever we actually have soft logic for, we could potentially roll into something like that. So that could be another interesting project to work on. Another bullet point here, RISC-V management core. This has been on my to-do list for a while, but I haven't had time to really properly engage with it. If there's someone who's interested in working with software, this is something that I would like to integrate into Corundum at some point in the near future. And the idea here is basically to take all of the board-specific stuff that we have in the device driver and push that into a soft core on the board itself. The idea being to make it so that if you're implementing a Corundum on a new board, you don't have to make any modifications to the device driver. So both the Linux kernel driver, the DPDK driver, any other third-party drivers that somebody might write, they don't have to be aware of what the actual board is, because they can just talk to the soft core using a standardized protocol of some sort, some sort of board-independent API.
What about grouping together the other soft cores and hard cores like the microblaze and NIOS and Zinc and whatnot?
Well, you mean why RISC-V instead of something else?
No, I just think in addition to the RISC-V, right, because they should be able to implement a microblaze or use the Zinc or the NIOS on cards that have it, right? I mean, this would definitely be just standalone.
I mean, kind of my thinking is that if we have something that's fully a soft processor and fully standalone, then it's going to make it easier to provide a similar, or not a similar, but an identical API, from the driver perspective across everything. If you use different soft cores, you might need to change some aspect about how that interface works. And these days, you can get some very, very small RISC-V cores, RISC-V soft cores to put down. Like I think the Vex RISC-V in particular is, it can be configured to be quite small and efficient. This doesn't have to be very high performance. So I don't think, even if you have like a device that also has a Zinc core available, which, I mean, certainly you could use that, or the internal.
I would lean towards a Pico Blaze or something similar, right? I mean, that's all you need is just something to read some registers and probe some values, do some I2C.
Right. Yeah. Yeah. I mean, the problem with Pico Blaze is that it's very specific to Xilinx devices. I think the last time I looked at the Pico Blaze, I think it's like manually constructed from LUT primitives, from Xilinx LUT primitives. So it's not very portable across different FPGAs. So using a more device independent RISC-V core, I think, would probably be more flexible from that standpoint. And the other thing is that if it's all running the same kind of base firmware, it makes it a lot easier to add new features to it, because the OS side interface code is, you could probably just use the same thing. If you have to make an improvement to that, you just need to rebuild all the code for all the individual boards. You don't need to individually update each piece of firmware, especially if you're running on different cores. It would make things easier to maintain by doing that.
Okay.
And then you also don't need to deal with vastly different build processes, right? So the RISC-V compiler and whatnot, that's, I think, a pretty standard thing to get your hands on, right? It's just GCC, and you don't need any particularly complicated libraries for it. If you wanted to use something like the Zinc ARM cores on Zinc devices, well, that might make it difficult to run Peta Linux on there for one, if you want to use it for management. How do you reconcile that? And then second, you might need a bunch of, Xilinx specific libraries to configure everything properly. It would just add a lot of complexity to the build process, I think. Yeah. I mean, I'm certainly open to, some different ideas here, but it just seems to me that having a little dedicated core just for the board specific interfacing, and doing that in kind of as a consistent way as possible is going to be the way to go. So, but yeah, it's basically just going to have some sort of interface to the driver that I haven't totally figured out exactly what that needs to look like. There's a couple of different references that I have in mind, but haven't really found the ideal solution there. And then on the other end, yeah, it's going to have I2C, serial port, GPIO, stuff like that for interfacing with a few parts of the design of Corundum, and then also whatever onboard interfacing is required. So yeah, I mean, I will say I'm not married to RISC-V, but I just think that's probably going to be the most straightforward way of implementing that.
Okay, yeah, I guess I just because I finally got that stupid Zinc thing integrated with the 250 SoC, so that's what I've been thinking about.
Right. Yeah. Well, the other thing is that you can always drop down more cores or whatever for application level stuff. So
right.
By keeping the management core separate from all of that, it should keep things more straightforward, right? Because, like I said, if you wanted to use a Zinc, you certainly could, but it might make it harder to use a Zinc for, application stuff. If we have a dedicated management core of some sort, then that means you can do whatever you want with the Zinc core.
Yeah, I'm a Xilinx guy, so I would have gone for a microblaze or a pico blaze if we're just mid banging registers.
Yeah, yeah, true. I mean, if Corundum only ran on Xilinx, I'd probably be like, yeah, sure, I guess we could do that. But because we run on both Xilinx and Intel devices, unless there's a way to build microblaze for Intel
is there
Express
an,
10 or Agilex or something.
yeah, is there an equivalent open source like pico blaze microcontroller that we wouldn't have to go full RISC-V?
Well, I mean, they make some very, very small RISC-V cores that could potentially be used. I know Vex RISC-V is highly configurable. So there's a bunch of different ways you can set that thing up, and some of those are quite small. I'm also aware of a core, I think, called the Serve, which is it's extremely small because it is bit serial. Well, it's also slow, but it is stupidly small.
Well, I've seen some that are in the 15 to 20,000 gates or levels. So there's definitely small ones out.
Yeah. It's not something I've looked into recently, but there's a lot of different RISC-V cores out there, and I guess the thing is we don't necessarily want to pick the absolute smallest one possible, although we certainly could. There might be a one that's slightly larger but also provides some useful features. Like I think there's a few RISC-V cores that support debug interfaces. I know the Vex RISC-V in particular does, but there might be a few others as well, where you can basically enable JTAG on that core, and then you can bring that out to user space somehow. I think we looked into this a while ago. How you could do debug access to RISC-V cores in the design somehow over PCI Express. There's a couple different potential routes that could be taken for that. And that would mean you can use, GDB single-step debugging type stuff, and you can very easily update the code on there.
What's the name of the core that you mentioned? What's this one?
What?
Which version of the RISC-V were you
mentioning? Which core did I have in mind, or what?
Yeah,
your audio is kind of dropping out.
Sorry, which version of the RISC-V were you mentioning? I didn't catch the name.
The Vex RISC-V?
Vex?
Here, I'll send you a link. Let's see. Right, there's the Vexus 5. And then there's also, let me see if I can find the other one. If you want something incredibly small, I think this is the probably the smallest RISC-V core available. Let's see, the serve is 125 LUTs and 164 flip-flops. So is it possible to make it smaller than that? Well, it's going to be hard. I think that might even be smaller than a PicoBlaze. I don't know.
Yes.
Honestly, probably what's going to consume more logic is not the core itself, but any of the interfacing stuff and associated memories and whatnot. So,
yeah, speaking of memories, where would you store the firmware for that RISC-V? Like onboard memory or somewhere external?
right. I guess there's a couple different options for that. Probably the simplest and most straightforward thing to do is just have it in block RAM, so it's initialized when the FPGA image is loaded, and then it can be integrated into the build process. But the flip side, it would also be possible to write it into the flash alongside the the bit file for the actual FPGA. But that does add a lot of additional complexity because you can't just flash the bit file now. You also have to flash the firmware for the RISC-V core, and okay, now you can't just load the thing over JTAG and have everything work properly. So,
right.
Yeah, I'm not married to doing something like that at this point. Although I guess what you can always do is potentially have, two copies of the firmware. One of them that's built into the bit stream and gets preloaded into internal block RAM, and then you could potentially have another copy of the firmware in flash, and basically a bootloader that goes and checks to see if it's there in flash. If it is, then it'll load that one. Otherwise, it'll run with whatever's been preloaded into the block RAM. That might end up being the most flexible thing, because then you could update the firmware without having to swap out the whole FPGA configuration just by writing that into the appropriate location of the onboard flash.
Right. Yeah, makes sense.
Yeah, a couple of options there. I guess another thing that you can do as well, depending on how we set things up, is you could potentially have the driver or user space tools or something overwrite the firmware in the block RAM, either via a debug interface. So if we have a RISC-V core or a Vexus 5 with the debug extensions, I'm presuming that you can use those to basically erase and update the firmware. I mean, obviously that wouldn't be persistent, but you could definitely use that for debugging. It's like load a new firmware, check to see if it works. Okay, that looks good. Then you can integrate it into the bit file build process for the FPGA. But that would allow you to very easily test out new functionality there.
Yeah, it seems like the ideal case would be have make it non-mandatory to flash the RISC-V core manually. Like,
yeah,
have users be allowed to not be aware that a RISC-V is there, but still have the option to do so if need be, right? But without reflashing the whole thing, right? I think that's what
yeah. Definitely, you don't want to make the whole process of flashing a new FPGA board more complicated than it needs to be. You can just flash the bit file, that's the way to go. And it's also nice if you can just load over JTAG and have everything work, because you could always run into situations where you've loaded a new design over JTAG, but for some reason the RISC-V loaded its firmware out of flash, and that's some other random version, or it got confused about something that was in flash and tried to load that. Yeah, it opens up a potential for a bunch of weird issues. So,
which is what happened with the the base platform for the Alveo boards, right? They ask you to flash a bit stream over this static part of the chip, and then they have some extra steps to flash all of the onboard microblazes that they have on top of there. So
because those all load their code out of Flash.
I'm not sure where they load their code from. So they've been, you can tell Xilinx has tried to make it transparent to the user, because the way you do it is you just run one command. I think that they call it XB management, something like that. And it does the two steps separately, but in one command from the point of view of the user. So yeah, they have like 4 microblazes on their thing.
You're not getting that mixed up with the MSP 430 that's on the board, right?
I think they have both. The MSP
right,
430
because they also
and
have
the
an
microblazes.
MSP 430 microcontroller that sits on the board.
Yeah.
That's not on the FPGA, but it's used for board management stuff.
Right.
And that would have to be flashed separately from the FPGA. And I think when you update the Alveo shell, it will potentially update that as well.
I think they have something in for both. Not sure how they implement it. Not sure.
Might be worth taking a look at.
Yeah.
Anyway, so that's one thing, and then I guess there's I have 2 other ideas on here that are pretty straightforward. So moving along, we've got the open source FTDI JTAG adapter, basically for Alveo boards. So if anybody is familiar with like the U50 or the SN1022, they don't have onboard USB JTAG. The JTAG accesses through some proprietary connector. So like the U50 has this 30-pin thing, and the SN1022 has this 60-pin high-density edge connector thing. Yeah. And if you buy the cable from Xilinx, it's kind of expensive. So, but the thing is, all you really need is the connector on a board. And then I realized, well, hey, half of the all the Digilent cables, they just have the FTDI FT4232 chip on there. So it wouldn't be particularly difficult to make a little board that has one of those FTDI parts, and then has a collection of different Xilinx JTAG connectors, right? The 30-pin connector for the U50, the 60-pin connector for the 1022, potentially other connectors. You could put their default 14-pin connector on there. And that, I think, even just getting a couple of those made would be a heck of a lot cheaper than, buying the cable from Xilinx. So I have an SN1022 that I'd like to get kind of running on at some point, but to do that, I need to put together a little cable. I haven't had time to work on that, but if somebody likes laying out boards and, has a need for something like this, I'd be happy to help facilitate and double check the connector pinouts and whatnot, just so we have a high confidence that it'll work. So that could be a little project for somebody. And then finally, we have an improved transmit scheduler. So right now in Corundum, the transmit scheduler is a very simple round-robin scheduler, which gets the job done, but it's also not very configurable in terms of what you can do. It would be useful to have something that could do, say, weighted fair queuing, rate limiting, things of that nature. That's something that somebody wants to work on. It could be, that could even theoretically be a whole research project in and of itself, building a much more complicated and expressive scheduler for NICs. I know there's a few different papers talking about different scheduler designs. It might be possible to take one of those and drop it into Corundum as a scheduler. So that's another potentially relatively self-contained project that somebody could chip away at. All right, so again, some project ideas here. If these sound interesting to anybody, and you want to work on it, let me know, and I'd be happy to do reasonable facilitation to provide whatever resources and support that you might need to get it done. All right, so moving on. If anybody has any questions or comments on these, just let me know via email or Zulip or whatever. Okay, so moving on to status updates. 3 main things: Mac control and PFC some updates to some AXI stream components, and then a few words on the current status of the Switch project. All right, so Mac control and PFC/pause frames. I'm not going to go into too much detail because, talked about this the last couple of meetings, but the Mac control layer is to exchange messages between the Macs themselves at the ends of a link. They're not really intended to be passed up to higher layers of the stack. These are used primarily for things like PFC and pause frame support, which are hardware flow control for Ethernet. So what I've been working on in the Verilog Ethernet repository is an implementation of PFC pause frame handling and Mac control layer handling. And I've integrated that into most of the Mac modules and tested that in hardware. Seems to be doing what it's supposed to do. The next step then is to take that functionality and integrate it into Corundum. And there's a few bits and pieces that I need to do in order for that to work. So that's what I've been working on over the past couple of weeks here. One thing that we need is the FIFOs need to report depth, or certain FIFOs at least, that can be used to generate the outgoing pause requests. And then for PFC, we need support for traffic classes. So that is going to be more complicated to implement. So I'm going to start with just pause frames, and then we'll circle back to PDP support, PFC support a little bit later on once traffic classes have been implemented and all that is working. Now, traffic classes and PDP and PFC kind of go hand in hand. It doesn't really make a lot of sense to implement traffic classes without PFC, and if you have PFC without traffic classes, it also doesn't really serve much purpose. Right. So to support some of these modifications, I've been making some changes to the AXI stream library. I added depth status outputs to the FIFOs, so both the synchronous and the asynchronous FIFOs now have outputs that indicate how much data is sitting in the FIFO. I also went ahead and added pause support to the FIFOs. So this only adds a couple of LUTs if you enable it, and it gives you a pause request input. So if you assert that, it'll wait till the end of the current frame and then block traffic from leaving the FIFO. So this can be used to terminate the pause requests for pause frame support, and it can also potentially be used to drain the data path on the RX side. So this can potentially avoid a few problems with taking links down. And also, if you have a Corundum design set up with multiple ports wired to the same interface, and you only want to use some of the ports, well, with this functionality, you'll be able to turn off the ports that you're not using. So that's useful. I've also been doing some reworking of the test benches of the FIFOs. Did a bunch of reorganizing and adjusting to try and get some stuff cleaned up, and I added some overflow drop tests. So this is for the FIFOs when used on the RX side, since they can't exert back pressure against the Macs. I mean, you can't really exert back pressure against the SerDes. It's just, you start getting data and you got to deal with it. If you get into a situation where the RX FIFO fills up, well, it has to start dropping packets, and you want to do that without corrupting packets and whatnot. So I added some tests to actually test that functionality. And I need to be able to test that because for kind of resource consumption purposes, what we want to do is shrink the async FIFO down to smaller than the size of a frame. And I'm calling this kind of a pseudo-elastic buffer support. Because on the TX side, you can ensure that the Mac is going to be getting frames contiguously, despite not being able to buffer the whole frame. And then on the RX side, we got to be able to, do the same thing and work with the buffer size that's much smaller than a frame size. So the question then is, how do you handle the overflow case? Well, what you have to do is mark that the frames are bad, and then because they've been truncated, and then downstream you can then drop the frame with a frame FIFO or something else. So now that I have the test bench code to actually test under these conditions, I now need to sit down this week and implement the logic in the actual FIFO to handle this. So hopefully that shouldn't take too much longer, and then I'll be able to get that integrated. We can shrink the async FIFOs in Corundum, which should save some logic resources and, well, save some block RAM anyway, and then we can use that block RAM in the synchronous FIFOs as part of supporting multiple traffic classes. Let's see. And the other thing that I was working on as well is a rewrite of the width converter. Previously, I didn't have it wasn't written in a very nice way, and it was consuming, we had multiple additional register slices that weren't required. So basically I combined the skid buffer and width converter logic into the same thing. So we basically have one register slice on the input and one register slice on the output, and seems to get the job done. And I think I have some more specific numbers on the Zulip. I didn't pull those up, but it actually, on a design where we have multiple ports on the same interface, it saves a pretty large number of logic resources. And I guess on all the 25 gig designs, there's also a 64 to 128 bit conversion that takes place using the width converters. So this will make that a bit smaller. So it's definitely going to be useful to have this change made on the switch, because that could potentially have a lot of ports that need to be converted between different widths. I've also been thinking about kind of merging the width converter logic into the FIFOs as well, because if that's merged into the FIFO, then you don't necessarily need another set of pipeline registers, of output registers or whatever, so you could potentially save a few more logic resources. I haven't done that yet, but I'm thinking about potentially doing that. All right, so moving on to the last thing I want to talk about here is the just high-level status updates on the switch. So I'm not sure if I mentioned that in the Corundum developer meeting, but we have the HTG 9200 FPGA boards that have 9 QSFP28s, and we have put together a design that brings up all of those ports, which is slightly non-trivial to do because there's SLR crossings between some of the GT cores and CMAX. Now that we have a nice soft wrapper that I put together for Corundum, well, we can just pop that on the HTG 9200. I'll put 9 of those on there, and seems to work reasonably well. I'm not going to say it's perfect, but it's decent. Sometimes Vivado doesn't do all that well with the placement, but that's a different problem. Right. So with that, we've been putting some relatively early crossbar designs onto the device to try to get an idea of how well things are working from a timing closure perspective and whatnot. So I think the main things we've done so far is we've tested a 4x4 switch that uses a single 4x4 sub switch. Now the thing to keep in mind with the sub switches that we're using is that they are memory-based switches, and they're designed for use with a higher frequency clock. So an n by n sub switch is intended for use with a speed up of n. So if you have a 4x4 sub switch, you should be running that at 4 times the clock frequency. But in this case, we dropped the clock frequency down to 2x, just to kind of get an idea of how well this core is working from a timing performance perspective. And naturally, if you're not running at the full speed up, you can't hit line rate with all the frame sizes, but it works as expected. So you can compute, okay, what's the expected rate that we're going to be able to get for this particular frame size, then you run at that rate. And, the predictions that we made were pretty accurate about where we would end up in terms of the throughput. So that looks pretty good. And then we also built a 4x4 switch using 4 2x2 switches. And so this actually has the expected speed up. The first time we tried this, it didn't work quite as expected. I think we had a bug somewhere, but I think more recently Carlos tried it again, and it worked as expected. So with all of the packet sizes that we tested, including minimum length frames and the known worst case size, everything worked correctly, including MQ frames, jumbo frames, and whatnot. So next up, we're working on an 8x8 design. And we're also screwing around with placement and timing constraints as well to try to figure out, well, I guess we're not so much screwing out timing constraints, but screwing out placement constraints to take a look at the resulting timing performance, and then we can optimize the HDL to make this thing run with a higher speed up. So I'm not sure what we're going to be able to ultimately achieve in terms of the speed up. 4x is, well, it's under the device Fmax, but that doesn't mean it's going to be achievable. So we'll see. If we can only get 2x, then we can only get 2x, but hopefully we can get at least 3x. So I don't know if Carlos wants to, mention anything about, fill in any more details here. I don't want to go into too much detail, but if you're interested in the development of the Switch, well, we're alternating weeks between the Corundum development meeting and the Switch meeting. So if you're interested in more details there, tune in next week, and Carlos can talk about things in much greater detail. And Carlos, I don't know if you have anything you want to add on the Switch status, just briefly.
Well, just to mention that right at this point, as you mentioned, the main problem is with the placement constraints. So the other day we were able to achieve some very low performance for this 8x8 switch without just looping back all the ports. Very low speed because there was some bugs. So we make it work, but when we just try to, it seems like the congestion is the main problem because of the, if you want to store whole frames at the input and at the output, and you want to place everything in the same part of the FPGA, you're not going to need timing. Also, we have to handle also some of those reset signals that were trying to get to very far points without replication because they were inferred in Vivado as BAFG registers. So in the end we had to be solving all of this running one by one. And now it seems to that we're going to the correct solution, but still we are not getting good performance yet, but probably very soon we will. And also just to mention that there are many stuff to do with the Switch. So as also Alex mentioned, if anybody wants to collaborate, it will be more than welcome because there are still, not only for the crossfire, but also for some of the computation logic and English logic that we will also need at some point some help. So everybody is welcome to.
Yeah, it's right now we're only working with really the actual switch part of the Switch, right? The crossbar and whatnot. But another component is actually figuring out, given packets that are coming into the Switch, determining how those need to be routed through the Switch. That's basically we're just calling that the route computation logic for now, and we're going to start out with probably a very, very simple Ethernet only sort of thing, right? Just looking at the Ethernet frames or the Ethernet addresses. We're not doing any higher layer stuff, at least for the time being. But that's something that somebody's interested in working on that and helping to implement parts of that. That is certainly something that we'd be open to help with. So, but yeah, for the time being, we've been wrestling with Vivado, I suppose, is probably the best description.
Yeah.
But yeah, progress has been getting made, just little by little. All right, that's about all I got for the status update slides for today. If anyone has any questions or comments, fire away. We'll open it up to discussion.
Hello.
Hello.
Hi, Alex. We are a team from Hong Kong, and recently we are porting project named HXDP, which is use a soft core to process packets, and we plan to port the HXDP into Corundum's framework. And the project is still on process, and we are planning to let you know, and we are doing such things, and maybe in the future we can synchronize something in this periodically meeting. And actually, I have a question to ask, because
fire away.
Most of us are actually, some of us is new for FPGA. So we actually new for FPGA. So we have a question, is that when we review some Corundum code and we find that some register will suffix with next, and we want to ask why there's such a pipeline design. We actually don't understand. So yeah.
Oh, okay. So basically that's a coding style where you have two different always blocks. One of them is combinatorial and one of them is sequential. So the combinatorial logic, it sets the underscore next signals, which are not actually registers, but those are, I mean, this is just an aspect of how Verilog works. They're defined as regs, but they're not actually registers. They don't end up as flip-flops. And then the synchronous always block will take those next intermediate values and store them into the actual registers, which gives you the reg signals. And that allows you to doing something like that has a number of advantages, which I could go into more detail if you're interested, but it's just kind of the coding style that's used in a lot of modules because it makes them a little bit easier to write. I guess as I can go into some of the advantages, but one of them is it allows you to use some of those next values inside of the combinatorial always block. So instead of, I guess you can do similar stuff in a sequential always block, but it's not very pretty because you have to mix the blocking and non-blocking operators, the non-blocking and blocking assignment operators. So it's not very clean to do it that way, but it is possible to do the same sort of thing. Or you have to replicate stuff, which is also not great. Or you have to use wires and assigns, which is also not great. It's hard to read. So just using this particular setup, I think, tends to be more readable. And the other thing is that I tend to use a lot of selective resets. So for some modules, you can just reset everything. It's not really a big deal. But when you have a module that has a very, very wide data path, well, if you can avoid resetting the data path and just reset like the valid signals or whatever, the handshaking and control stuff, then it means you have a much less loads on the reset line. If you have separate always blocks for combinatorial and sequential logic, then it makes it very easy to only reset what needs to be reset without making things really hard to read. If you put it all in one always block, then it presents a bit of a problem because if you don't do it right, you're either you have to reset everything, or you can accidentally add connections to the reset net that you don't want. And that can just make the logic much more complicated than it needs to be. So just with this particular coding style, seems to work pretty well.
Yeah, okay, I see. Thank you. Yeah, this is actually a question that when we review the code and we discuss this coding style, and yeah, I see. So yeah, thank you. And this is my question. Yeah.
Yeah, I've definitely heard other people having very different ideas in terms of how to write HDL. But I don't know. This style seems to work pretty well for me. So
okay.
Yeah, I guess it's like when you're writing HDL, there's kind of a few different levels that you can work at. So I figure it's probably a good idea to try and work at the highest possible level, if you will. So yeah, you could certainly drop down AND gates and OR gates and XOR gates and flip-flops individually and interconnect them, but why? It just makes things really hard to read.
Yes.
Some people like coding that way. I'm like, okay, you can do that, but reading that code sucks. Hard to maintain. you're not taking advantage of HDL if you're writing stuff like that. So anyway, enough of an aside. Yeah, if you have any other questions, feel free to ask. You can ask at these meetings. You can ask on GitHub. You can ask on Zulip. Just whatever. But yeah, so you guys are working with HXDP. Are you familiar with a company called Axbrid at all?
No, we are just trying to we are trying to inject the XDP project into the app framework provided by Corundum. Yeah, and currently we are only we are hard coded the HTTP binary into the hardware, and we are implement the data path only, and the control plane we are still not started yet. Yeah, so yeah, we are still working on it, and currently we are able to reject packets using HXDP program, but for more complicated logics like if you're going to conduct some counting or like some complex filter logic, and we still cannot achieve it. Yeah, so maybe in the future we can have some ability like this. Yeah, so we are planning to let you know that we are doing such things, and maybe in the future we can share some progress with you.
Yeah, that would be very cool.
Yeah.
Yeah, I just wanted to mention Axbrid because those are the guys behind the HXDP paper, and I know they're using Corundum as a basis for implementing HXDP or whatever the current version of it is. It's like undergoing active development, but I think it's not open source necessarily. They're doing this internally with their company. So,
okay.
Yeah. So, so what is your guys' goal? Just to implement that, or are you going to extend it, or?
We are planning to we are going to build a prototype that we have a 100 gigabits NIC, and it has some soft core on it, and we are planning to implement something like we are optimizing RPC system that maybe we can doing some scheduling things on the NIC, and this is our goal. But the open source version of XDP, the actually open source version that runs on a net FPGA, and it has only 10 gigabits MAC, and we found it's not necessary and it's not sufficient for the data center applications. So we are porting our own versions. Yeah.
Okay. Yeah, I mean, I'm not sure on the HXDP side how much improvements they've made on that front. I'm trying to think if maybe they had a couple of different code bases that they released, because I know they had the net FPGA version. They didn't release anything on a more recent FPGA board. So all the work they've done with Corundum, I guess, is closed, or did they release a version on top of Corundum? It's been a while since I looked into that.
Yeah, we haven't found the latest version. We only found the open source version released by the paper.
Gotcha. Okay. Yeah, because I know they released that. I'm not sure if they released something newer, but maybe not. Maybe I'll take another look at that, see if I dig anything interesting up.
Yeah. All right. We appreciate it.
Well, it'll be interesting to hear how that goes.
Yeah. We might be share something in the future if we have some further progress. Yeah.
Right. And like I put in all of the emails I send around announcing these things, if you want to present something, let me know, and I'd be happy to give you a few minutes at the meetings to present whatever it is you're working on. So
okay.
There's no obligation to do that, but we would certainly be happy to listen if you want to talk about something. So
yeah, well, we're very willing to. If we can view such a prototype, we definitely will go here to share with everybody. Yeah.
All right. Well, looking forward to it.
Okay. Yeah. Okay. Thank you.
All right. Does anyone else have any other questions or comments, or anything you want to discuss? We had a good discussion on RISC-V cores earlier. Certainly revisit some of that. I don't know if there's any other cores worth mentioning. there was a Vex Risk 5 and a Serve. I guess there was also the was it the Pico RV?
Yeah, there's a Pico one in there. Hold on.
It was a Pico RV32? Yeah, okay, that's another one. I think that one is not under active development at the moment. Yeah, no updates since January 2022, but that's another one. That one I think is fully Verilog. So Spinal H, so Serve, I can't remember what that one was written in off the top of my head. Spinal HDL, or the Vexorus 5 is written in Spinal HDL, and then they could generate Verilog from that. Pico RV2 is written directly in Verilog. I know there's a couple of other cores that are written in System Verilog and a couple that are written in VHDL. Whatever route we take, I think it's got to be compatible with the current test framework. So if we can run this thing under Icarus Verilog and Verilator, that would be great. But unfortunately, that kind of rules out the VHDL cores, because they have the, was it Neo RV32? Yeah, that's another one. This one is actually a pretty cool project. It's written totally in VHDL. It's got the RISC-V core along with a bunch of SoC peripherals. So it looks pretty good, but unfortunately, we can't run it with the current simulation framework that Corundum uses. Unfortunately, there are no mixed language simulators. So until that changes, unfortunately, won't be able to use the Neo RV32. But it does look like it would be a very good option. Does this also have debug via JTAG? Yeah, it does have a JTAG interface there for debug. So along with a bunch of internal peripherals. So that one is more like, unlike some of the other cores, that one is almost like a complete microcontroller that you can just drop down with all the integrated peripherals and whatnot.
So can you just include those links in the slides?
Oh, I guess I could do that.
Yeah, just so we got them on record.
Yeah, that's a good idea. I'll go ahead and I guess I can just add another slide to the presentation real quick here. Yeah, I'll go ahead and do that.
And the only other thing I'd add to the list is, with these Oculink PCIe cores that I'm using, somewhere down the road, if we want to talk about how do we integrate these additional PCIe connections.
Right. Yeah. That's definitely something worth looking into.
Just throw it on the project
there's
list.
A couple of different things. Right. Yeah. Oops. I linked serve twice, or did I? Oh no, I screwed up my copy. Okay.
I mean, right now I'm just going to wire in a separate master slave into the app block from the Zinc, and probably have the Oculink just go straight into that PS DDR space. But I kind of feel like there should be a little more thought put into it than what I throw together on a Friday night.
Right. Yeah. I mean, so I guess there's a couple different directions some of this could be taken in. So this is one thing that I've been mulling over a little bit, is that if you have, multiple PCI Express interfaces, or like a Zinc or other large high performance core on the FPGA, how do you integrate that with the rest of the design? And ultimately there's a couple different directions that could go in. One of them is I could certainly see just adding a few pass-through interfaces to the application section for interfacing with, core that sits on the board. Because under certain situations, you probably just want to use that directly from the application block. But the other thing that I think I've talked about before at some point is basically the ability to share the Corundum, core data path between, multiple hosts. And my thought is that once we have the framework in place for SRIOV, that we could potentially use that to support multiple host interfaces. So the idea is that basically if you had an on FPGA core, then that could effectively get few PCI Express virtual functions. Even though the connection is not PCI Express, it would behave in a similar way, where you'd have these you could attach another couple of driver instances on the card to these VFs, and then presumably the master physical function on the PCI Express interface facing the host. You could then figure out which queues you want to allocate to these virtual function but not virtual function things. So with that set up, then you could direct packets to the host or to the Zinc, or if you have multiple PCI Express interfaces connected, you can stripe them across the multiple interfaces. It opens up a lot of possibilities, hopefully in a relatively self-contained way. But to implement that properly does involve a number of modifications to the Corundum core design, because we got to keep track of, for each operation that we're performing, which interface that's associated with. So, for SRIOV, you'd be keeping track of which virtual function, but the generic case is to, keep track of, I think it was calling it address spaces. So each virtual function would have its own address space, its own set of bars and whatnot. And then each, if you have two PCI Express interfaces, well, okay, that's just another set of address spaces. If you have, an AXI interface to a hardcore, like on a Zinc, that would just be another address space or several. So you have to add those sideband signals and then set everything up to manage the routing appropriately. So that's kind of a long-term thing that I've been thinking about. But yeah, the problem with something like SRIOV is, it's one thing to implement that on the host side, but without, some sort of a more complicated switching logic to classify packets and figure out which, virtual function to send them to, or which queue to send them to based on addressing or whatever, instead of just the current RSS implementation. It's not particularly helpful. So I think possibly with the packet switch project, we'll be putting together some logic that can do this sort of thing, this kind of classification, and we can use that both for the packet switch and for Corundum to implement some of this type of capability. So,
okay,
yeah, this is something that I've been thinking about. Architecturally, how could this possibly work? But it's
yeah,
kind of a longer-term thing to get all the kinks worked out of it.
Yeah, so the thing I'm trying to do is I'm trying to do some packet inspection, right? And with the Zincs, I want to use the app block to do a lot of the sort of pre-filtering and extraction, and then put the key data into the address space on the Zinc and let the four cores over there, chug through this stuff. And so, the problem is, well, what do you do with the packet in the meantime while it's got to sit in a buffer somewhere, and then pulling it back out, right? So, assuming we're looking for some anomalous byte string, right? I can FIFO or buffer the packet in the PL, but we send this data across it, and when it comes back and says, yes, that's a bad packet, being able to go back and kick it out of the queue somewhere is the piece I'm struggling with.
Yeah. Well, so the flow of data in that case, it would be coming in from the QSFP. It would then get handed off to the Zinc, which would then take a look at it and do some, you do some pre-filtering, right, which may require dropping the packet, and then you hand it off to the Zinc, which is going to do some stuff. And then at that point, either you drop it or you send it to the host?
Yes.
Okay.
So I could use multiple queues. Could have one queue, which is basically the cell phone waiting lot at the airport, right? Where packets go to hang out, but then somebody's got to be, draining that and sticking that into a queue that can actually go to the host every time we get a thumbs up or a thumbs down from the Zinc cores.
Yeah. I mean, I guess, yeah, that's an interesting. Yeah, what else could you do there? I mean, I guess ultimately what you could do is send the packet basically both to the host and to the Zinc, but then not do the handoff to the host until the Zinc has cleared the packet. Yeah, but
I don't want to send anything to the host that's bad, right? That's the whole thing we're trying to avoid. I don't want to be another DPDK or
right.
U-ring kind of application. I
Right.
want to actually do the work on the card.
Right. Well, so I'm trying to differentiate between two different things here. One of them is actually just writing the data out into host memory somewhere, and second one is actually doing the handoff and saying, here's a packet that you need to start your receive processing on.
Yeah, I still don't want to do that because we don't want to take up bandwidth to the host on stuff that eventually has no use. And in our case, we're looking at 90% throwaway, right?
Well, right. I mean, what I'm thinking about is, just where would you store those packets? And the host has a whole lot of really cheap DRAM. So, that would be a good place to store stuff potentially. But that could complicate things quite a bit in terms of how the data path is set up, because I don't think the Corundum data path is really set up to handle something like that, where you transfer the packet through to the host memory and then you just drop it on the floor. But then, yeah, if you're trying to, reduce the bandwidth across the PCI Express interface and not transfer these potentially malicious packets.
And I'm using the PS.
Yeah, that wouldn't really help.
So, yeah, the PS DDR is used to store signatures, so I can't buffer anything on the PS side.
Right,
plus,
and then you also
plus it's too slow.
Of throughput. Yeah, so there. I mean, I know on the 250 SoC there is PL DDR as well, but I don't know. Well, I don't think you have 100 gigabits per second worth of that either. So
no, I don't think so. 64 bits times, what is it, 2400?
Is it one bank or two banks? Well, either way,
I thought it was two.
I think it's probably not. Well, okay, two banks of that.
Take a look and see.
Yeah, maybe two banks is enough if you kind of merge those together. But yeah, I mean, okay, I guess you could use both of those for packet buffering, which would work. Would that be enough throughput? Maybe.
Anyway, I just throw it out there in case anybody else has ideas or opinions.
Yeah. Let me see what is on that card.
One bank in each.
Okay. Yeah, it's a small card. I guess they don't have space for two. So I think if you had two banks, you might be able to buffer 100 gig link. But with only one, that's more problematic.
Okay.
Yeah, I guess that's a 72-bit interface, just a single one. So with ECC, but yeah. Yeah, I know on a bunch of other boards they provide two, and some boards even provide four. So definitely a lot of throughput.
Well, add it to the list. See if anybody wants to jump on board, offer ideas.
Right. Yeah, I could certainly do that. All right. Well, does anyone else have any questions or comments or anything you want to discuss? If not, then I guess we can adjourn for today. And if you're interested in switch development, you can tune in next week. If you're interested in just Corundum, well, you can tune in 2 weeks. All right. Sounds good. I guess nobody has anything to add, so
Thanks.
See you guys in 2 weeks.
All right, bye.
See you. Thank you.
Talk to you.